Let us now prove a theorem. First, the statement of the theorem. Shear is equivalent to two equal strains an extension and a compression. Along two mutually perpendicular directions. We will explain it, but let us rewrite it in a bit different way first. A shear is equivalent to an extension coupled with an equal contraction at right angles. To each other. We first explain this theorem and then we'll prove it. Consider a cube and let us draw one face of the cube. So this is the face of the cube and this end is fixed. So this end is fixed. This face has two diagonals. And this is the other diagonal, and obviously they are at 90 degrees, so they are mutually perpendicular. Now, keeping this end fixed, let us apply a force at the other end of the cube, or this face of the cube. As a result, this point comes here and this point goes over there. In other words, this side is now distorted and it comes over here. So it is rotated by an angle theta, or we say it is sheared by an angle theta. So this is the original position or configuration of the cube or cubic face, and this is the distorted or deformed position. So the cube is sheared. Now what does this shearing mean? Let us investigate the distortion that this diagonal suffers. As this point comes here, this diagonal now goes over to here, which means this diagonal has been shortened or compressed, and the amount of compression can be found out if we draw a perpendicular from here, and this is the amount of compression. So this is the amount of compression. Compression or contraction which this diagonal suffers as the cube is sheared. Let us now find what happens to this diagonal. Since this point goes over here, this diagonal is now extended, and if we drop a perpendicular, then it follows that this is the amount of extension which this diagonal suffers. So through this simple drawing, we have proved already that as the cube is sheared, one diagonal gets compressed and the other diagonal gets elongated. The amount of compression has been shown, the amount of elongation or extension has been shown. Another point is that this compression and this elongation have occurred in the diagonals which are mutually orthogonal or mutually perpendicular. So this is what the theorem says. Let us read it once again. Shear is equivalent to two equal strains. One is an extension, which is this one. One is a compression, which is this one. And they occur along mutually perpendicular directions because the diagonals are mutually orthogonal. So one diagonal has been extended and the other diagonal has been contracted at right angles. Let us now prove this theorem. Though things are very much evident already as we draw this diagram. Let us prove it. Name the cube A, B, C and D. So the cube is A, B, C, D, and it is sheared to position A, B, C prime and D prime. So this is the new position of the cube and this one is the old position of the cube before shearing. Vector F, which is here, is the tangential force applied to upper end Theta is the angle of shear. The lower face AB is fixed and the upper end is DC. Due to this shearing, ABCD goes over to ABC prime D prime, and ABCD is actually a square and ABC prime D prime is actually a rhombus. We also note that the diagonal AC has been extended to AC prime while the diagonal BD has been contracted to BD prime. To find the amount of extension, the perpendicular C, say E, has been constructed on the diagonal AC prime and the amount of extension is EC prime. So let us write by extension of amount EC prime, as we dropped a perpendicular CE on AC prime. The amount of compression of this diagonal BD can be obtained by dropping a perpendicular D prime F on BD, and the contraction amount is DF. So BD is shortened to BD prime by this amount, and this was obtained since we dropped a perpendicular D prime F to the diagonal BD. Let us write down the strains. The compressional strain is dF is the compression or amount of contraction, and the original length is BD. So it is dF by BD. And the extensional strain is the amount of elongation or extension is EC prime, and this strain has been suffered by the diagonal AC. So the original length is AC. We here note that this BD and AC are mutually perpendicular. And they are strained. So let us also note that the lengths that suffer strain are AC and BD. Let us now have a careful look at this triangle. So this was the square, original square, and these are the diagonals, and they are perpendicular. So this angle is 90 degrees, and obviously this angle is 45 degrees, and so is this one. Now, due to shear keeping this end fixed, this diagonal comes here, and this diagonal goes over here. And then what we did was to drop a perpendicular. This was point D, this was D prime, and this was F. Now clearly this is 90 degrees since this is a perpendicular, and therefore this angle is 90 degree minus 45 degree, 45 degrees, which means that this triangle has two sides equal, which means it is an isosceles triangle, and one angle being a right angle, we can call it a right angled isosceles triangle. So D prime F, this triangle we have proved to be a right angled isosceles, means having two sides equal, and dF is equal to D prime F. So cosine of this angle, that is D prime dF, which is 45 degrees, so it is actually cos 45 degrees. By definition, it is base by hypotenuse, and base is df and hypotenuse is dd prime. So df, which is the amount of change in length or contraction, is dd prime into cos 45, which is 1 by root 2. Again, so BD square is equal to AD square plus AB square. And this side is L, this side is also L. So it is just L square plus L square equal to 2L square. So what we get is BD equal to L root 2. Now the compressional strain is dF by BD. dF is this one, BD is this one. So we have so this is what we get for compressional strain. Let us now find out the extensional strain. So the amount of compression that we got is dd prime by twice L. So it is dd prime by twice L, where L is the length of the cube. We will now find the amount of extension, that is C prime E. Let us draw the cube once again. And this is the diagonal that suffers extension when we keep this end fixed and apply a force, tangential force, along this direction, as a result of which this side is tilted and it comes here, this side is also tilted and it arrives here. So this is the new position of the cube. Now this being a square and this being a diagonal, this 90-degree angle is being bisected by this diagonal, as a result of which this angle is 45 degrees and so is this angle. So this is 45 degrees and this is also 45 degrees. The extended diagonal is this one, which is actually the diagonal of a rhombus, and this diagonal therefore bisects this angle, corner angle of the rhombus, which means this angle and that angle are equal. Now the shear is of amount theta, so this is theta, which means this angle is 45 minus theta. And let us suppose that this angle is x. This means that this angle is 45 minus theta plus x. Again, this is 45 degrees and this is x, which means this angle is 45 degree minus x. To find the value of x, therefore, we equate this and this angle to get, which is this one, should be equal to this angle, which is 45 degree minus x. So simplification gives us twice x equal to theta. 45 degrees cancel out and therefore we end up with x equal to theta by 2. To find the amount of extension, we drop a perpendicular from this point C, and this was E, and this was C prime. Now this being 90 degrees, it being a perpendicular, the value of this angle is 90 minus x. So this is 90 minus x. Again, this is a square and this is a diagonal of it, which means this angle is 45 degrees. So now we are in a position to find the value of this angle. So this is the entire angle at this point is 180 degrees. And from it we have to subtract 45 degrees as well as 90 minus x. So this gives 45 degree plus x, or in other words it is 45 degree plus theta by 2, because x is theta by 2. Again, this being 90 degrees, the sum of these two angles has to be 90 degrees, which means this angle is therefore 45 degree minus theta by 2, and if we add them we get 90 degrees. We now make a vital approximation that things are being done within elastic limit. That is, this tangential force is small, so the shear is small. So theta is small. So theta by 2 is smaller and therefore can be neglected. Theta is small and it is as good as 0. In other words, things are done within elastic limit. F is very, very small. So the angles 45 degree plus minus theta by 2 can be taken to be 45 degree, and therefore this triangle becomes an isosceles triangle under this assumption. So C, E, C prime for theta tends to 0 or small shear becomes a right angled, because this angle is 90 degrees, isosceles triangle. So since the angles are equal to 45 degrees, these sides are assumed to be equal, and therefore it becomes a isosceles right angled triangle. And therefore let us write it as 45 degrees for theta tends to 0. So let us find the cosine of C prime E, that is this angle, which is as good as 45 degrees, that is 1 by root 2. So it is, as per definition, base by hypotenuse. So it is EC prime by CC prime, and therefore EC prime turns out to be CC prime into 1 by root 2. The extensional strain is EC prime by AC. The value of EC prime is this one. Let us find the value of AC. Now from this triangle ACB, using Pythagoras theorem, we have AC square equal to AB square plus BC square, and AB is L and BC is L, and therefore we have 2L square. So AC is equal to L root 2. The extensional strain is therefore it is EC prime by AC, and EC prime is CC prime by under root 2, while AC is L root 2, and therefore it turns out to be CC prime by twice L. So let us go back to the initial diagram, and the extension that we proved is CC prime by twice L. Of course, under the approximation that theta is very, very small. So it is a small shear case. We now focus our attention to these two triangles ADD prime and BCC prime, because we have to show that CC prime and DD prime are equal. So from triangle ADD prime, let us find the value of tan of theta, and tan theta as per definition is perpendicular by base. So it is DD prime by base is AD, which is equal to L. So it is DD prime by L. Again, from triangle BCC prime, the value of tan theta is CC prime by BC. So it is CC prime by BC is L. So it is L. The left hand side for both the equations is tan theta. So it follows from here that DD prime and CC prime are equal. Now DD prime occurs in the compression and CC prime occurs in the extension. So let us write these relations. And further, they are equal to half of tan theta. Also, as shear is very small, tan theta can be replaced by theta, and therefore the compression and extension, which are equal, is equal to theta by 2, where theta represents the angle of shear. Angle of shear. So let us write as a gist. So this is theta by 2, and this is also theta by 2. So as a gist we can write a shear of amount theta is equivalent to 2 strains at right angles to each other. One is called tensile strain, or longitudinal strain, and corresponds to this extension case, and the other one is called compressive strain, which is also equal to theta by 2, and this corresponds to the compression. So this is the theorem.